we're going to talk about energy here. So I can get this a little more clear. There we go. All right, so we kind of talked about energy a little bit. I know my class we talked about kinetic energy a little bit. So what is energy? Okay, so energy is just the ability to produce change in an environment. The ability to produce change in an environment. Right? Like if you want to lift something up on top of something else, you have to have energy in order to do that, right? All right, and what the energy we're going to start with is mechanical energy. And that is just the sum of potential and kinetic energy. So it's the energy of like motion kind of that we're going to be talking about here. Okay, our formula for mechanical energy is just that PE plus KE. Okay, all of our energy is going to be measured in joules. In joules, that's mechanical, potential, kinetic, all the different type of energies measured in joules. Okay, so we're going to start off with what is potential energy. Okay, we have two different types we're going to talk about. The first one is gravitational potential energy. So kind of just like it sounds, it deals with gravity, right? So objects stored, so I guess objects, okay, stored potential energy when an object is held off the ground. In other words, has a height. Give me 1 second. All right, so anything that has a height. So in other words, it's like the potential to fall. So you have the potential energy, and we have a little subscript G, just to say we say it's gravitational potential energy. It's going to be mass times gravity times height. All right, so for example, you lift a 2 kilogram textbook from the floor to a shelf 2.10 meters above the floor. What is the book's gravitational potential energy? So once it is lifted, once it has a height of 2.1 meters, it also has a mass of 2 kilograms. We want to know what is the gravitational potential energy. Okay, so gravitational potential energy is equal to mass times gravity times height. We know the mass is 2. We know gravity is, we use negative 9.8. I know it a lot in my class, but if we're talking about energy, you're not going to have a negative energy, right? Kind of like you don't have a negative mass or negative time. So go ahead and leave that as a positive 9.8. It's going to have energy if it has height. 0.8 times 2.1. So I'm going to multiply those up. The textbook up on the shelf has a gravitational potential energy of 41.16 joules. Okay, 41.16 joules. And if it was to fall, that's how much energy it would be losing. Well, not really losing, you can't lose energy, but it would be converting that to that kinetic energy that's going to be causing damage on whatever it falls on. Okay, the other type of potential energy we have is elastic potential energy, and that's stored energy. Stored energy in an object. An object when undergoes a change in shape. Okay, so think of like your bow and arrows, right? Whenever you stretch it, you're changing the shape of it. And when you do that, it now has energy stored in it that it can be released into that arrow, right? To shoot the bow and arrow. So we do PE, the subscript S, because it's kind of, we do it for the spring part of it. Okay, equals 1/2 K is a spring constant. Okay, that's not going to change. That spring constant is dependent upon the spring itself. Think of like a trampoline spring. Okay, they're really, really hard to spread apart. Okay, so that trampoline spring would have a high spring constant. But then you think of like the spring found in your little mechanical pencils. It's a really, really easy spring to manipulate, right? To change the shape of. So it'd have a really, really low spring constant. So that just depended on the spring. And then distance from the equilibrium, how far did you actually stretch it or compress it or push it together, right? How much did that spring actually change? Or in this case, the bow and arrow. All right, a 60-kilogram boy jumps on a trampoline, compressing the spring 25 centimeters. If the spring has a constant of 85 newton meters, how much elastic potential energy does the boy have? Okay, I know I'm given a mass. I'm given a distance from equilibrium, so how much it's compressed, 25 centimeters, that's 0.025 meters. I'm given a spring constant of 85 newton meters. How much elastic potential energy do we have? 1/2 kx squared. Okay, notice that we're given a little bit extra information, right? Don't need to know the mass in this case. Doesn't matter. So 1/2 0.5 times 85 times 0.25 squared. So 0.5 times 85 times 0.25 squared. Elastic potential energy is 2.66 joules roughly. All right, so those are two types of potential energy. Now let's talk about the kinetic energy. So for kinetic energy, it's just the energy of an object in motion. Has a velocity. Yeah, formula for that is Ke equals 1/2 mv squared. All right, so an 875 kilogram compact car speeds up from 22 to 44 meters per second while passing another car. What were its initial and final energies? Okay, so both were moving. So let's do the initial first. So we have a mass of 875. We have an initial velocity of 22. All right, that's all we're going to need for our formula. 1/2 mv squared, so 0.5875 times 22 squared. And then we'll do the same thing, but with our final velocity. So 0.5875 and final squared. Don't forget to square your velocity. That's number one mistake that I see. All right, so I went ahead and did it. 211,000 versus 847,000. So did the Ke double when we doubled the velocity? Nope, it quadrupled. Nope. Why? Because that velocity is squared. Okay, so again, keep that in mind. Flipping over. Okay, kind of more conceptual. Talking about what do we have, all right? So zero means we have none, non-zero means we have some. We don't have much, we have some. So a satellite in orbit, do we have kinetic energy? Yes. Do we have potential energy, gravitational? Yes, we have the potential to fall, right? That's height. A boulder resting at the bottom of a cliff, okay? If it's just resting, it doesn't have any speed. And if it's at the bottom of a cliff, it doesn't have any height. A car parked on top of a hill, well, it's parked, so it's not moving, but it does have height. It's on top of a hill. Yeah, law of conservation of energy. Notice that we did COE this time instead of COP, conservation of energy. All right, and that just states that energy cannot be created nor destroyed, only changed or transferred. Which means that if we have like potential energy, it can't just go away. It'll be converted into kinetic energy or a different type of energy. All right, so formula, if it's a conservation, remember that everything is saved, which means that the total initial energy that a system has will be equal to the total final energy that the system has. In other words, you can also say it's mechanical energy, right? Because mechanical is just the sum of those two energies of the potential and the kinetics. And if we were to write it out even more, we would say that potential energy plus kinetic energy, which is both initial, just mechanical, is equal to the potential energy final plus the kinetic energy final. Kind of the same way we did whenever we had the MV1 plus MV2 all the initial on the left side and all the final on the right side, same idea. For example, Tarzan stands on a 20-meter high cliff and swings on a vine to the jungle floor below. If he has a mass of 85 kilograms, how fast does Tarzan swing when he reaches the jungle floor? Okay, so let's look at what we're given here. We're given a height of 20 meters, and he swings on the vine to the jungle floor below. Okay, so his initial height is going to be 20 meters. His bottom height is going to be 0, right? If he has a mass, so initial height 20, final height 0. If he has a mass isn't going to change, 85 kilograms. How fast, so final velocity, is he swinging and reaches the jungle floor? Well, if he's standing on top of a cliff, his initial velocity is also 0. All right, so if I was to look at this, do PEI plus KEI equals PEF plus KEF. Okay, at the very beginning, did he have potential energy? Yes, because he was standing on a cliff, right? Did he have kinetic energy? No, because that initial velocity was 0. Okay, so we're just going to scratch it out. At the end, he's on the jungle floor, so he no longer has potential energy, but he does have kinetic energy because he's going to go, and how fast is he going? So our formula now becomes PEI equals KEF. Pretty easy to work with at that point. Mass times gravity times height equals 1/2 mv squared. Sorry. Mass was 85. Gravity again, we're going to keep it positive. Height of 20 equals 1/2 mass of 85, and we're solving for that v squared. So everything on the right side, 85 times 9.8 times 20. Left side is 16,660 equals 1/2 of 85 is 42.5 times v squared. I'm going to divide by 42.5. 1660 divided by 42.5. I get 392 equals v squared. Take the square root. Nope, wrong button. 392. And I get a velocity of Tarzan, a final velocity of 19.8 meters per second. So if he used all that gravitational potential energy and converted all of it to kinetic energy, he'll be traveling 19.8 meters per second when he hits the jungle floor. Okay? All right, and on number 2 and number 3, okay? What I want you to do on these, because class is about to start, go ahead and go into those copy and notes, or attempt first, and then go into the copy and notes and see if you can figure it out. If not, come see me and I can help you with those.